So, yes, my thesis is called Non-Classical and Chaotic Motion of Two-Dimensional Light. And in this work, I studied two very distinct phenomena and tried to answer on two main questions. The first one is how fast can a particle move within a classically forbidden region, or in other words, tunnel. And the second question is in what ways can classical chaos manifest in quantum systems. So let's start with quantum tunneling. Quantum tunneling is probably one of the most known phenomena from quantum physics, and it was studied basically from since inception of quantum physics itself, so for almost 100 years. And the idea is that in classical mechanics, the particle can surmount the potential barrier if and only if it has enough energy to do that. Otherwise, it will be just bounced off. And in quantum mechanics, there is always a non-zero probability for particle to surmount the potential barrier, even if it doesn't have enough energy to do that. And probably many people are aware that this year's Nobel Prize in Physics was given for the discovery of macroscopic quantum tunneling in superconducting circuits for the experiments that were done more than 40 years ago. And people show that actually quantum effects can be observed in macroscopic systems. And I think, in my opinion, this year's Nobel Prize highlights the importance of fundamental research. Despite the fact that tunneling was well studied and understood, some aspects of tunneling still unclear. For example, speed of tunneling particles or tunneling time. And in our work, we measured speed of tunneling particles, and this is our measurement scheme. The most important part of this scheme is that we have coupled waveguides, and the second important part is that we can inject particles with different initial energies, so we can probe both classically allowed motion, so propagation inside potential step, and also classically forbidden motion, so decay in solution in potential step. And just by analyzing particle density inside coupled waveguide region for different initial energies, we can restore speed of tunneling particles. And in this case, coupled waveguide scheme, namely coupling constant, plays a role of a clock to measure speed. And this is our main result. Speed versus kinetic energy inside the potential step delta. And on the right hand side of the graph, you can see positive delta, which represents classical motion. And on the left hand side, you can see negative delta, which actually represent quantum tunneling. And here we can see that the lower the kinetic energy inside the potential step, so the more negative kinetic energy of particle, the faster they move, or the higher their velocity. And this is our main result. And this is actually very counterintuitive. And moreover, our speed measurements can be considered as a possible test for Bohmian interpretation of quantum mechanics. Shortly, for classically forbidden motion, Bohmian mechanics predicts zero velocity, but as we saw from the previous slide, our measured speed is not equal to zero. This actually attracted a lot of media attention. For example, science communicator Sabine Hassenfelder even made a video about that. And the second topic, which is studied in my thesis, is chaos. Chaos is usually represented as a butterfly effect when tiny changes can lead to huge consequences in complex systems. For example, butterfly flapping its wings somewhere in South America can trigger a storm somewhere in Japan. In terms of classical mechanics, it means the existence of sensitivity to initial conditions leading to exponential divergence of closed initial trajectories. And in quantum mechanics, actually, we have uncertainty principle, so we do not have a notion of initial conditions and trajectories. But at the same time, we have correspondence principle, which tells us that for large quantum numbers or for large energies, quantum mechanics should give same prediction as classical mechanics. And this suggests us that there should be some physical mechanism that can give rise to sensitivity to initial conditions in quantum systems. And that's what we tried to measure. We used a so-called quantum wedge billiard system, which you can see here. And we, in our system, could excite a lot of different states inside this wedge. And actually, this red circle represents pump spot position, so the position at which we can excite different states. And the idea was to compare two excitation schemes. The first one is resonant pumping, so the first picture, and we can see if we change pump spot position, the dynamics is overall smooth, and we do not see big changes in modes. But if you have a look to non-resonant optical pumping, we immediately see that overall the dynamics are very different, and we can see these uncorrelated mode jumps when we change pump spot position. So here we really show that it's possible to find a mechanism, like physical mechanism, which will trigger sensitivity to initial conditions or classical chaos in quantum systems. And let's summarize. In the first part of my thesis, we measured the speed of tunneling particles, and in the second part, we observed a transition between quantum and classical forms of chaos. And thank you for your attention. Thank you for coming. I'm glad to see all of you. And I hope you will enjoy the defense.